Hello and welcome back to the Science Corner. Today's video will be covering the second part of the glycolytic pathway, or what I've been calling it, the payoff phase. In the first part, we converted glucose into two molecules of glyceraldehyde 3-phosphate, invested two molecules of ATP, and now in this phase of the reaction, in the payoff phase, we'll receive two additional, or four total, ATP molecules for an overall yield of 2, and we'll end up with our final product for this pathway of that being pyruvate. Okay, so here we're just going to start off with reaction 6, that is the conversion of glyceraldehyde 3-phosphate into 1,3-bisphosphoglycerate. This is catalyzed by glyceraldehyde 3-phosphate dehydrogenase. And similarly to most of the reactions, excluding reaction 1 and reaction 3, the delta G, or free energy change, for this reaction is basically 0, meaning that depending upon your substrate, depending upon the concentrations of either glyceraldehyde 3-phosphate or 1,3-bisphosphoglycerate, the energy can flow in either direction. Again, that's based on the law of mass action, also known as Le Chatelier's principle. So in this reaction, we have first time we have seen and will see a redox reaction. That is the reduction, the oxidation of this aldehyde group off of glyceraldehyde 3-phosphate into an azophosphate over here on the 1,3-bisphosphoglycerate. And so whenever there's an oxidation, there has to be a reduction. No electrons are lost, they are only transferred. And so the electrons that we lose here on glyceraldehyde 3-phosphate from this hydrogen to become a hydride, is tossed onto our electron acceptor NAD+ to make NADH, and then a proton is lost into solution. An also interesting note here is that we are actually attaching another phosphate group through phosphoric acid and not ATP. And the reason we can do this is because oxidation reactions are extremely exothermic. They release a lot of energy. So instead of releasing the energy as heat, like we see with a lot of reactions, burning of fuel and such, we are going to capture that energy and use that to make this high energy molecule with its azophosphate off of carbon 1. Okay, so again, to recap, we are creating a high energy molecule to make ATP in the next reaction. Believe it or not, 1,3-bisphosphoglycerate is has a lot more energy in it than ATP does, which is why we can extract, as you'll see in the next reaction, one of these phosphates off to make ATP. It's a downhill reaction, it's favorable. And like I've said, it's the only redox reaction in the pathway. And so I just wanted to go over the mechanism because I think it's very interesting. It's not necessarily to know, but I'm going to go over it. It is a attack by the thiol group off of the cysteine from the enzyme, attacking the carbonyl-carbon, pushing electrons up onto the oxygen. This is our formation of our aldehyde to our acid, and of general base, probably hydroxide or something similar. Picks off this hydrogen, electrons from that bond are shuttled back onto the carbon-oxygen bond to reform our double bond, and our NAD+, acting as an electron sink, pulls off the hydrogen from that central carbon. The reason this acts as an electron sink is because not only do we have conjugation occurring here in this ring, but we have a positively charged nitrogen group, which we want to quench that positive charge, and so we're able to shuttle electrons into this molecule forming our NADH. With our reformation of this carbonyl and the stabilization by this thiol bond, phosphoric acid is able to attack the carbonyl carbon, push electrons back up onto the oxygen, and then we again will reform our enzyme by pushing electrons from this oxygen back onto the carbon-oxygen bond, and then push the enzyme off of the substrate, forming the product of 1,3-bisphosphoglycerate. Alright, reaction 7, also known as our break-even reaction. This is our first reaction where we perform substrate level phosphorylation. That is the removal of one of the phosphate groups to make ATP through an enzyme. Okay, so here in reaction 7, the break-even reaction, we have 1,3-bisphosphoglycerate being converted into 3-phosphoglycerate. We pick off the phosphate group off carbon 1. Surprisingly, this is at equilibrium as well, a common theme in the glycolytic pathway, catalyzed by phosphoglycerate kinase. And again, we form ATP, but not just one. Remember, we had 2 molecules of glyceraldehyde 3-phosphate from 1 molecule of glucose. So we are creating 2 molecules of ATP, hence the break-even reaction. So this just kind of describes how the enzyme is laid out and works. So at the N-terminus we have 1,3-bisphosphoglycerate binding, and at the C-terminus we bind ADP. Upon them both binding, we get a conformational change. The two are brought close together where the chemistry happens. We get a hinge bend. Bring the two substrates close in proximity, the chemistry can occur. This is such a high energy molecule that because of the acyl phosphate we have here, a lot of energy can be released upon removal. We're left with the carboxylic acid on C1, and remember, and it's important to note that the second bottom half of the molecules here are not touched during these two reactions. It's all this chemistry is occurring on carbon 1. Okay, the next reaction, 3-phosphoglycerate to 2-phosphoglycerate, has an important function. It may seem like a pretty simple and kind of useless reaction, but you'll see how moving up the phosphate group from carbon 3 to carbon 2 creates a molecule with even higher internal energy than that of 1,3-bisphosphoglycerate. So 3-phosphoglycerate is converted into 2-phosphoglycerate by phosphoglycerate mutase. Again, delta G is close to 0. Reaction can flow in either direction fairly easily, depending upon our concentrations of substrate and product. And the reason we are moving the phosphate from carbon 3 onto carbon 2 is because in the next reaction we are going to form a enol form of this 3-carbon molecule. And to kind of recapitulate that, let's just kind of go over what an enol is. Typically, we know what a ketone is. Ketones have a carbon with a double bond to an oxygen and some other atoms coming off of the central carbon to make our four bonds for that carbon. And it can isomerize to an enol form. And our enol form is when electrons are pushed onto the, let's just make that distinguish as different than this R group. When electrons are pushed down onto between the carbon and its substituent, other than the oxygen. So it could look like this. Commonly, there's actually another carbon here. Oops. Commonly, there is another carbon here. So it looks something like that. Sorry for that extra bond. And the enol form of these molecules is significantly less stable than that the ketone form. So what we're going to do here is, you can kind of see, we have our carbon 2 and our carbon 3, and here's an oxygen bound to carbon 2, kind of similar here. You can think this is our carbon 2 and our carbon 3 and our oxygen bound to our carbon 1, or sorry, our carbon 2. And what we're going to form is an enol. And so that is what's going to allow us to form, that's going to form a high energy intermediate, which we can then convert into a ketone form to release energy and actually make more ATP. So that's why this conversion of 3-phosphoglycerate into 2-phosphoglycerate is important, because you want this phosphate group, this phosphate group, to be on a carbon that has, it's a secondary carbon, not a primary carbon. And reaction 9, we're doing exactly that. Conversion of 2-phosphoglycerate into phosphoenol pyruvate. The enol form of pyruvate, basically converted by enolase. We lose some water. Again, the delta G is close to 0. Phosphoenol pyruvate is also commonly called PEP, P-E-P. And we're doing exactly as I stated before. You convert, we're forming a double bond between carbons 2 and carbons 3, locking in this enol form, which has a very, very high internal energy, even though the metabolic energy, that is the kinds and the types of molecules, atoms we have bound within this molecule remain the same. It's the organization of the electrons relative to these atoms which leads to its high potential energy. So like I stated, enol versus keto tautomerization, the double bonded C and O is highly favorable to that of the double bonded CC. Okay, so now that we have this high energy intermediate in the final reaction of this pathway, the glycolytic pathway, we are going to convert our phosphoenol pyruvate into pyruvate through pyruvate kinase. This is the last reaction, and its delta G is significantly negative. That is negative 23 kilojoules per mole at under physiological conditions. That's how much energy is released, showing you the energy potential that this molecule harnesses. And so with all this energy release, we can couple that to ATP synthesis. So we have a conversion of ADP into ATP, and remember this is going to be 2 ATP because we have 2 molecules of each, 2 molecules of PEP. So we have an overall net yield of 2 ATP for this entire process. Similarly to reactions 1 and 3, because the free energy change is so negative, we have regulation that occurs on this enzyme. Inhibitors are ATP and acetyl-CoA. You'll see acetyl-CoA is the pyruvate is converted into acetyl-CoA for the next process of oxidative for aerobic respiration, which is then shuttled through the citric acid cycle. So if you have accumulation of acetyl-CoA, your citric acid cycle is backed up. Let's wait off on this energy releasing reaction until it's needed. ATP is an obvious one. High ATP will inhibit the enzyme because we don't need the ATP. Let's not waste this energy if we don't need it at this time. And activators, AMP, kind of because if we don't have a lot of energy around, we have a lot of higher concentrations of AMP compared to normal, so we need to make more, so this reaction goes forward. And also fructose 1,6-bisphosphate, having to do with the reverse pathway of the glycolysis, which is gluconeogenesis. When we need to form glucose, we have excess pyruvate around, we can convert our pyruvate into glucose for storage, and so that's kind of how this is an activator for this forward reaction, because fructose 1,6-bisphosphate is one of the intermediates upstream of gluconeogenesis. So if you have high levels of this, it will push the reaction forward, and the reverse is not as unfavored. So just to summarize the overall reaction we did here in these 10 steps, remember, we're converting 1 molecule of glucose into 2 molecules of pyruvate. On the way, we harvest some energy in the form of 2 ATP and a couple electrons, carriers of NADH. Now this whole reaction yields a lot of energy if it's all done in one step, but we've done this in a series of smaller steps, so these reactions are reversible. If we did this all in one step, this would be an irreversible reaction, which would just lead to a high release of heat energy and a loss of a lot of this potential energy to heat instead of converting into high energy molecules such as ATP, which can be used for other cellular processes. Okay, so that's glycolysis, and look forward to the next series of reactions, all involved in aerobic respiration, that is the citric acid cycle, and after that we will be discussing the electron transport chain, where we really are able to convert a lot of ADP into ATP, much more than glycolysis can provide. Thanks for stopping by.